Hello and welcome to video 1.2, Measurements and the Metric System. I'm Mrs. O'Neill and this video is intended for the physics class at Goessel High School. Thank you for finding my video. Let's start talking about what measurements are for. Measurements are the fundamental method that we use in order to start reasoning out the relationships between the objects and phenomena surrounding our lives. We do this by applying numbers to them. Once we have numbers, we can do quantitative analysis, which is based on numbers. Examples of quantitative analysis include things such as using mathematical formulas to make predictions, or creating graphs to detect trends. It's not an overstatement to say that measurements are a cornerstone of science. Without good measurements, you don't have good data, and without good data, you're not doing good science. There's a few things that all measurements have in common. First of all, they all have to have an agreed upon magnitude or scale. What does that measurement even mean? A foot here in Kansas has to be the same size as a foot in California or in Washington, D.C. or anywhere else. Otherwise, people won't be able to compare data from different locations and reach meaningful conclusions. As part of that, we have to label our data. We have to, in addition to having the numbers involved, we have to have the units too. If you're just giving me numbers in your data, then your data is wide open for misinterpretation. If I say that from here to Newton is 13, well, if you didn't know, that could be 13 miles, or 13 kilometers, or 13 hours. Alright, and then finally, and this is perhaps more complicated, all measurements have built-in uncertainty. How correct or how accurate the measurement is, or how incorrect or inaccurate. And that is because there is no measurement possible that's going to exactly match up against reality, surely due to the limitations of our tools. We don't have rulers that can measure down to the nearest atom. We don't have scales that can measure to the nearest atom, and so we're always going to have to round off, and that creates built-in uncertainty. And the amount of uncertainty has to be kept in mind when we're analyzing our data because it can completely overwhelm the conclusions that we're trying to draw from the data. As part of this, when we're talking about data, we do need to keep in mind the difference between precision and accuracy. These two terms are considered to be interchangeable in our common day-to-day language, but in science they have very distinct and different meanings from one another. Precision is the repeatability of a measurement. If you do it over and over and over again, will you get the same number or close to the same numbers? Accuracy, on the other hand, is how correct you are, how close you are to what's accepted as the true value. You can have precision without accuracy. For example, if you're taking measurements on a scale in a lab and you didn't zero out the scale, then you've introduced a consistent error into your measurement. All your numbers might be very, very similar to one another, but they're all going to be wrong because that 0 point wasn't in the right spot. On the other hand, if you have data that's accurate but not precise, usually that's due to hurried or careless measuring. You're just in a rush, and so your data is around the correct value, but it's got a wide range. Ideally, our data will be both precise and accurate. Alright, as we're taking these measurements, we have to keep in mind what measurement system we're working with. These systems are just interlinked sets of measurement units that are expected to go together, and there are two major systems that are used here in the United States. The first one is just known as the standard system, and it is our official United States system, but it is not used throughout the rest of the world. Because of that, it makes it very difficult to collaborate with other people. The standard system itself is kind of unfriendly, but we're very familiar with it. This is the system we learned in kindergarten. Length is composed of inches, feet, yards, and miles. Volume is cups, quarts, and gallons. Mass is in pounds and tons, stuff like that. We're very familiar with them, but mathematically they're hard to work with. There's not a consistent jump between the units. It's 12 inches to 1 foot and 3 feet to 1 yard. I don't know how many yards are in a mile, but it's 5,280 feet in a mile, and that number is just pretty random. It's hard to do math with. If I wanted to know how many inches were in a mile, I'd have to take 12 times 5,280, and it's not very flexible. If you wanted to measure bacteria, we don't really have anything smaller than an inch, and so we'd be working with very, very tiny fractions or numbers with lots and lots of zeros. And for all these reasons, we don't use the standard system in science very much. Instead, we use what's called the metric system, which was developed in the late 1800s in order to create a logical, easy system of measurement that could be used worldwide. It's also known as SI, International System of Units. The S and I are reversed just because it was named originally in French. And then, like I said, this one is widely accepted. It's used worldwide, so scientists from all different countries can collaborate and share data. Mathematically, it's a lot easier to work with because it's base 10, which means it's the same mathematical structure as the way that we write our numbers. Instead of having to do multiplication or division to do conversions, all you have to do is move your decimal point around, and it's far, far easier. And because of these reasons, this metric system is nearly always used in science and medicine, and in this classroom. The metric unit for length is a meter, which is roughly equivalent to a yard. If you have to think yard every time you hear meter, that's fine. It's a good equivalence. A volume is in liters. Liters we're probably the most familiar with because of soda pop coming in 2 liters, so half of a 2 liter is a liter. And then mass is in grams. A gram is a very small amount of mass. It's roughly how much a ladybug weighs, and so we usually use kilograms when we're talking about bigger things. Kilo being a metric prefix that makes the grams bigger. And these prefixes are where the metric system really comes into its own and greatly increase the flexibility of the system. We can change the size of the unit to be as big or as small as whatever it is we're trying to measure. Milli, for example, is 1/1000th. Centi is 1/100th, and deci is 1/10th. Then we come to our base unit, meter, liter, and gram. Then deca is 10, hecto is 100, and kilo is 1000. To be honest, we only really use these 3, milli, centi, and kilo, very often in class, as well as the base units. But these other 3 we do have to keep in mind because we need to know that they're there in order to move our decimal places the right number of steps. So you do want to be able to remember milli, centi, deci, base unit, deca, hecto, kilo. The easiest way to do that might be with a mnemonic, such as, mother can't decide, but you don't hate kangaroos. I made that one up. There's lots of other ones you can use if you want, or you can even make up your own. Mother is obviously milli, centi, deci, but U stands for base unit, deca, hecto, and kilo, so it all fits. We can also use a visual representation called the metric ladder in order to do simpler conversions. This is the metric ladder. It just has those same prefixes arranged in boxes on a slope here, so we can go up or down the ladder. You are going to want to copy this into your notes somewhere. It's very helpful to have when you're doing homework or doing labs. It makes conversions much more simple. Let's look at some examples on how to use the ladder, and then we'll be done with this video. For our first example, we want to convert 35 liters to centiliters. We're going to start at our base unit. Since it's just one letter, that means that it does not have a prefix and it is the base unit. If it's got 2 letters, then there's a prefix involved. So we're starting at our base unit and we're going to go down to centi. So 1, 2 jumps to the right. We want to move our decimal point in the same direction and the same number of jumps. Now the decimal point isn't super obvious here because it's invisible, but that doesn't mean it's not there, and we can just draw it in. So we have our decimal point and we're going to move it 1, 2 jumps to the right. We jumped into nothing, there's nothing here, but we can just fill it in with zeros, and that's alright too. So our answer here is 3,500. Please don't make fun of my handwriting in these videos. I'm using a mouse, and so it's always going to be terrible. Alright, our next example. 45 milligrams to grams. This time we're going to start down here at the bottom and go the other way. 1, 2, 3. Starting at milli up to grams is 3 jumps to the left. Our decimal point is still right here, but this time we're going the other direction. 1, 2, 3. Here's our new decimal point. We're going to need to put a 0 here where we have that empty space, but we're also going to want to put a 0 in front of your decimal. Please never put naked decimal points in your homework problems. They're very difficult to see, and it may cause me to misgrade your homework, and none of us want that. So I don't like them being naked. Put zeros on them. They're happier that way. One more example, and then we'll be done. From 0.02 kilometers to centimeters. We're going to go really far this time. So starting here in kilo, 1, 2, 3, 4, 5 jumps to the right. Here's our decimal. 1, 2, 3, 4, 5 jumps to the right. We have a 0, and a 0, and a 0 right here. And now that we've moved the decimal, we don't need these 2 zeros anymore. With no decimal in between them, they don't signify anything, and we can just take them out. So we're starting with the 2, followed by 3 zeros. Alright, and we're done with our notes. Don't forget that you do need to take the quiz over this video. The link can be found in the video description below if you're on YouTube. If you're on the website, the link is also available directly below the video. Or if you really just lost, there's a document in the Google Drive for this class called Video Quiz Links, and it'll also include the link there. When you do take the video, you need to be logged into your school Gmail account at that time in order to have access to the form. You want to make sure that you're logged into your own account and that you're not logged into anybody else's account for any reason, or I'll receive the quiz in their name and not yours, and you will not get credit for it. So double check that you're logged in and double check that it's in your name. All right, thank you for watching the video, and I'm looking forward to seeing you in class again soon.